Billions of years ago, Venus may have been Earth's twin, a world of blue skies, vast oceans, and the potential for life. Today, it is a planet of extremes, its surface hotter than molten lead and shrouded in clouds of sulfuric acid. How did a world so similar to Earth transform into a fiery wasteland? Could the same forces threaten our own planet? Join us as we unravel the story of Venus, Earth's closest neighbor, and its most haunting warning. In the vast expanse of the solar system, two planets emerged with striking similarities. Venus and Earth, nearly identical in size, mass, and composition, were born alongside each other, forged from the same cosmic dust and gas that orbited the young sun. Both planets were initially cradled in a region of space that seemed perfectly suited to nurturing life. Venus, bathed in sunlight slightly stronger than Earth's, may have once been the world of rivers, lakes, and oceans. Its early atmosphere could have been dense with water vapor, creating a cradle for life much like that of ancient Earth. But today, these two planets are worlds apart, each telling a radically different story. Venus has become a planet of extremes, its surface a desolate, volcanic wasteland smothered by a thick atmosphere of carbon dioxide. The air is so dense that standing on Venus's surface would feel like enduring the crushing weight found nearly a kilometer beneath Earth's oceans. Temperatures soar to a searing 475 degrees Celsius, hot enough to liquefy most metals. Above, thick clouds of sulfuric acid churn relentlessly, trapping heat and shielding the surface from view. It is a world where no spacecraft has survived more than a few hours, a place utterly hostile to life as we know it. Earth, in stark contrast, is a vibrant oasis in the void. Its surface teems with life, nourished by oceans of liquid water and protected by a thin, life-sustaining atmosphere. From dense forests to vast plains, from the deepest oceans to the highest peaks, Earth has cultivated an intricate web of ecosystems that have evolved and thrived for billions of years. This stark divergence between two planets, so similar in origin, raises profound and urgent questions. How could two seemingly twin worlds have followed such drastically different paths? What critical events or forces pushed Venus toward a hellish fate, while allowing Earth to remain a haven for life? These questions lie at the heart of planetary science, and hold the key to understanding not only our solar system, but also the potential for life elsewhere in the universe. Venus offers scientists a unique and haunting case study. Its history tells a cautionary tale of planetary fragility and the fine line between survival and annihilation. Long ago, Venus may have enjoyed a temperate climate, with its oceans acting as a stabilizing force for its atmosphere. But something changed. A tipping point was reached, and the balance was lost. The oceans boiled away, releasing vast amounts of water vapor into the atmosphere. This greenhouse gas trapped heat, accelerating the planet's warming. As temperatures climbed, Venus's surface underwent a catastrophic transformation. Its water disappeared into space, its carbon dioxide levels skyrocketed, and volcanic activity reshaped the landscape into the barren, scorching terrain we see today. Scientists now recognize Venus as an example of a runaway greenhouse effect. This phenomenon, where rising temperatures create feedback loops that drive further warming, offers a sobering glimpse into how quickly a planet's environment can spiral out of control. By studying Venus, researchers hope to learn more about the mechanisms behind such drastic changes and how to prevent similar outcomes on Earth. Venus serves as a mirror, reflecting the potential vulnerabilities of Earth's own climate system and reminding us how delicate the balance of habitability truly is. Yet Venus is more than just a warning. It is also a gateway to understanding the broader forces that shape planets. By comparing Venus and Earth, scientists can uncover the subtle but critical differences that determine a planet's fate. Was it Venus's slightly closer position to the Sun that sealed its doom, or were there other factors, such as its thick crust or lack of a magnetic field, that made it unable to regulate its atmosphere? The answers to these questions not only deepen our knowledge of Venus, but also refine our understanding of what makes a planet habitable. As humanity expands its gaze beyond the solar system, the story of Venus becomes even more significant. Thousands of exoplanets have already been discovered, and many of them are Earth-sized worlds orbiting their stars in regions that appear suitable for liquid water. But Venus teaches us to look beyond surface similarities. A planet's size and location are only part of the story. Beneath the clouds, a seemingly Earth-like world could conceal an uninhabitable inferno. Understanding Venus is crucial for interpreting the planets we find around distant stars, and for identifying those that truly hold the potential for life. The tale of Venus and Earth is one of contrast and consequence, of survival and collapse. It is a story of how two worlds, born with such promise, could diverge so drastically. For Earth, it is a reminder of the forces that have shaped its stability and the importance of preserving that delicate balance. For Venus, it is a testament to the unforgiving power of planetary processes that can render even the most promising world barren and lifeless. By exploring Venus, we do more than uncover its mysteries. We take a step closer to understanding the intricate web of factors that sustain life on Earth and beyond. The lessons Venus holds are not just about the past, they are about the future. Of Earth, of exoplanets, and of our place in the cosmos. This is not simply the story of two planets, it is a profound reflection on the fragile balance that determines whether a world will nurture life or succumb to chaos. To look at Venus from afar is to see a planet shrouded in beauty, its brilliant glow dominating the morning and evening skies. It is often called the evening star, or the morning star, a celestial beacon of light second only to the moon in brightness. Yet beneath its ethereal glow lies a world of extremes, a planet so hostile and unforgiving that it defies all notions of habitability. The air on Venus is an oppressive force, composed of 95% carbon dioxide, with traces of nitrogen and other gases. This dense atmosphere exerts a crushing pressure on the surface, equal to being nearly 900 meters below Earth's oceans. Moving through such an environment would feel more like swimming through a thick, stifling liquid than walking on solid ground. The weight of this atmosphere is unrelenting, pressing down on the surface with an intensity that no human could endure. Even more daunting is the heat. Venus's surface is the hottest of any planet in the solar system, with temperatures soaring to an average of 475 degrees Celsius. This searing heat is a direct result of the runaway greenhouse effect, where the thick carbon dioxide atmosphere traps immense amounts of solar radiation, allowing little to escape. At these temperatures, lead melts, and even the toughest materials struggle to maintain their integrity. Above the surface, thick clouds of sulfuric acid swirl in chaotic patterns. These clouds, opaque to visible light, create a dense, impenetrable veil concealing the planet's surface from view. Lightning crackles through the upper atmosphere, illuminating the churning clouds with brief flashes of energy. Beneath them, winds sweep across the planet at hurricane speeds, circling Venus in a phenomenon known as superrotation, while the planet itself rotates sluggishly, taking 243 Earth days to complete a single spin. Its atmosphere races around it in mere days, creating a dramatic contrast between surface and sky. Rain on Venus is not the kind of rain we know on Earth. It is composed of droplets of sulfuric acid, corrosive enough to dissolve metal. Yet, before this acid rain can reach the surface, it evaporates in the intense heat, creating a cycle of precipitation that never touches the ground. The planet's clouds act as both a barrier and a furnace, trapping heat and creating an environment that is not just uninhabitable, but lethal. Exploring Venus has always been one of humanity's greatest challenges. The conditions are so extreme that no spacecraft has survived on its surface for more than a few hours. The Soviet Venera missions of the 1970s and 1980s managed to send landers to Venus, capturing images and transmitting data before the crushing pressure and blistering heat rendered their instruments useless. These fleeting glimpses revealed a landscape like no other. A barren, fractured surface, littered with sharp rocks and volcanic formations, bathed in an orange glow from the dense atmosphere. Beyond these early efforts, the only way scientists have been able to study Venus is through radar mapping from orbiting spacecraft. NASA's Magellan mission in the 1990s used radar to penetrate the thick clouds and map nearly the entire surface of Venus. What it revealed was a planet shaped by relentless volcanic activity, with vast plains of solidified lava, towering mountain ranges, and strange, tessellated terrains. But these images only deepened the mystery. How did Venus come to be so drastically different from Earth? Venus's atmosphere also poses challenges for understanding its climate. Without a protective magnetic field like Earth's, Venus's upper atmosphere is directly exposed to the solar wind. This steady stream of charged particles from the sun strips away lighter elements, such as hydrogen, into space. Over time, this loss has eroded what little water may have once existed on the planet, leaving it dry and barren. The absence of water has halted the carbon cycle, a natural process on Earth that helps regulate atmospheric carbon dioxide levels. Scientists describe Venus as a cautionary tale of what happens when a planet loses its ability to maintain balance. The carbon dioxide that pours from volcanoes on Earth is absorbed back into its oceans and rocks, creating a self-regulating system. On Venus, this system broke down, leaving a one-way accumulation of carbon dioxide in the atmosphere. Despite its extreme conditions, Venus remains a subject of fascination. Its hostile environment challenges the limits of human ingenuity and technological resilience. Each mission to Venus must contend with crushing pressure, scorching heat, and corrosive clouds, pushing the boundaries of what is possible. Yet the rewards of exploring this enigmatic planet are immense. Venus holds secrets about the past that could reshape our understanding of planetary evolution, not just in our solar system, but across the galaxy. Studying Venus is not just about looking outward. It is about reflecting inward, understanding what made Earth habitable and what could threaten that balance in the future. By facing the challenges of Venus, we gain insights into the forces that shape all worlds, including our own. Venus is often described as a planet of contradictions. While its surface is a searing, crushing wasteland, hidden beneath its thick veil of clouds lies a landscape that is as captivating as it is deadly. The dense atmosphere conceals an alien world shaped by volcanic forces, with geological features that rival the complexity and beauty of Earth. Radar mapping, particularly from NASA's Magellan mission, has provided scientists with detailed glimpses of Venus's surface. These images, though rendered in shades of gray, reveal a planet sculpted by immense volcanic activity. Venus's plains stretch for thousands of kilometers, covered in solidified lava flows that intertwine like rivers of stone. Towering above these plains are massive shield volcanoes, some of which are among the largest in the solar system. These gentle giants rise gradually, their slopes extending outward for hundreds of kilometers, resembling shields resting on the ground. Other features are even more enigmatic. Vast highland regions, known as tessera terranes, are some of the oldest surfaces on Venus. Their name comes from their intricate tile-like patterns, which resemble the tessellated floors of ancient Roman villas. These tessera are thought to be composed of rocks that formed billions of years ago, possibly in environments once dominated by water. Some scientists speculate that these regions could hold clues about Venus's early history, when the planet may have been more Earth-like. Venus's volcanic diversity is unlike anything else in the solar system. Its pancake domes, unique to the planet, are flat-topped formations with steep edges that spanned tens of kilometers. These domes are believed to have formed from highly viscous lava that oozed slowly to the surface, creating a shape that is eerily smooth and circular. Some of these domes have collapsed or fractured, giving rise to formations that scientists have nicknamed tick, due to their resemblance to crushed insects or spiderwebs. Perhaps the most striking volcanic features on Venus are its corona, enormous ring-like structures formed by plumes of molten rock rising from the planet's interior. These plumes push upward, distorting the surface into concentric ridges and fractures, sometimes stretching across hundreds or even thousands of kilometers. In some ways, corona resembles the calderas of Earth's volcanoes, though their scale and complexity are far greater. Despite the inhospitable conditions, some scientists describe Venus's surface as breathtakingly beautiful. The interplay of volcanic forms, valleys, and channels carved by ancient lava flows creates a landscape as dynamic as Earth's, but alien in every sense. The radar images hint at a strange elegance, a world where the forces of creation and destruction have left their intricate mark. Venus's geology is not static. Evidence suggests that the planet may still be geologically active, with ongoing volcanic eruptions reshaping its surface. Heat escaping from its interior creates a restless, dynamic environment beneath the crust. This makes Venus one of the few places in the solar system where volcanic processes may still be occurring, a phenomenon that offers a window into the planet's inner workings. Yet this beauty is not without danger. The lava flows on Venus are not shaped by water or wind erosion as they are on Earth. Instead, they exist in a world where the atmosphere itself becomes an oppressive force. The thick air slows the descent of molten rock, allowing it to spread in ways unfamiliar to terrestrial geologists. Combined with the planet's intense heat, these processes create a surface that is both alien and hauntingly majestic. For scientists, the allure of Venus's surface lies not only in its beauty, but also in the secrets it holds. The tessera terranes may preserve a record of Venus's distant past, when it was a very different world. If Venus once had oceans, those waters may have interacted with its surface to form minerals or other geological markers that remain embedded in the tessera. Unlocking these records could reveal whether Venus was ever capable of supporting life and why its fate diverged so dramatically from Earth's. The highland plateaus of Venus, such as Istar Terra and Aphrodite Terra, add further intrigue. These elevated regions resemble continents, suggesting that Venus once experienced geological processes similar to plate tectonics on Earth. Their wrinkled and folded appearance points to immense forces at work, possibly related to the planet's volcanic activity or the movement of its crust. Exploring this alien world has been a challenge, but new technologies are offering fresh possibilities. Advanced radar systems and high-temperature electronics could one day allow landers to survive long enough to study Venus's surface up close. Until then, scientists rely on orbital data to piece together the story of a planet that is as enigmatic as it is mesmerizing. Venus's surface, hidden from the naked eye by its toxic clouds, is a testament to the power and unpredictability of planetary evolution. Beneath its hostile exterior lies a world of intricate landscapes and geological wonders, a silent reminder of the forces that have shaped and destroyed its potential for life. Long before humanity understood the true nature of Venus, its dazzling light captivated ancient sky watchers. As one of the brightest objects in the night sky, Venus inspired myths, legends, and stories across cultures, becoming a symbol of beauty, power, and mystery. Its ability to appear in the morning or evening, never straying far from the sun, made it an object of fascination and reverence, deeply entwined with humanity's earliest understandings of the cosmos. To ancient Asian sky watchers, Venus was seen as two distinct stars. In the morning, it was called the beginner of brightness, a herald of the coming day. In the evening, it was the exalted western one, a symbol of twilight and the transition into night. These dual appearances gave Venus a role as a celestial messenger, straddling the boundaries between light and darkness. The Sumerians identified Venus with Inanna, their goddess of love, fertility, and war. To them, Venus's shifting visibility symbolized the duality of Inanna's nature, gentle yet fierce, nurturing yet destructive. Inanna's mythology often depicted her descending into the underworld and returning, mirroring the way Venus seems to disappear and reappear in the sky. The Greeks and Romans carried these ideas forward, associating Venus with Aphrodite and her Roman counterpart, Venus, the goddess of love and beauty. According to Greek mythology, Aphrodite was born from the foam of the sea, a symbol of creation and allure. To the Romans, the goddess Venus represented fertility, prosperity, and the essence of human desire. According to the goddess of Venus dedicated to her, such as Veneralia, a celebration of love and purity held in April, which was named in her honor. Across the Atlantic, the Aztecs, Maya, and other Mesoamerican cultures saw Venus in a completely different light. To them, Venus was a fierce warrior, a celestial power locked in a cosmic struggle. The Aztecs associated Venus with Quetzalcoatl, the feathered serpent god who descended into the underworld to bring enlightenment to humanity. For these cultures, Venus's movements in the sky were tied to cycles of warfare and sacrifice. Its rising and setting marked the timing of rituals and battles, emphasizing its role as a divine force of reckoning. These varying interpretations reflect the deep cultural significance of Venus throughout human history. Whether as a symbol of love and fertility, a messenger of the gods, or a warrior descending into the underworld, Venus has always been more than just a celestial object. It has been a canvas onto which humans projected their hopes, fears, and understanding of the cosmos. As humanity transitioned into the scientific age, Venus's mythological identity began to give way to observation and inquiry. The planet that had inspired gods and legends became the focus of telescopes and early astronomical studies. In 1610, Galileo Galilei observed Venus through his telescope, discovering that it exhibited phases like the moon. This discovery was revolutionary, providing concrete evidence that Venus orbited the sun and supporting the heliocentric model of the solar system. A century and a half later, in 1761, the Russian scientist Mikhail Lomonosov observed a rare event called the transit of Venus. As the planet passed directly in front of the sun, Lomonosov noticed a subtle distortion of light at its edges. From this observation, he deduced that Venus must have an atmosphere. This was a groundbreaking discovery suggesting that Venus might share some characteristics with Earth. Venus's brightness and proximity to Earth sparked imaginations. During the 19th and early 20th centuries, writers and scientists speculated about what lay beneath its clouds. Early science fiction often depicted Venus as a lush, tropical paradise teeming with life. The thick clouds were assumed to be made of water vapor, and the planet was thought to harbor vast jungles and prehistoric creatures. For a time, Venus was imagined as a second Earth, waiting to be explored and understood. As space exploration advanced, these romanticized ideas about Venus gave way to harsh realities. The first missions to Venus, such as NASA's Mariner 2 in 1962 and the Soviet Union's Venera series in the 1970s, revealed a planet far more hostile than anyone had imagined. Instead of jungles and rivers, scientists discovered blistering heat, crushing pressures, and an atmosphere saturated with carbon dioxide. The dream of Venus as a second Earth was shattered, replaced by a new understanding of its extreme environment. Yet, even as Venus's scientific identity emerged, its cultural legacy endured. The planet continues to inspire, reminding us of humanity's long-standing relationship with the stars. Its mythological and historical significance adds depth to our understanding of its scientific reality, connecting the stories of the past with the discoveries of the present. Venus remains a celestial paradox, a beacon of beauty that conceals a hostile world. Its mythology and history reflect humanity's evolving relationship with the cosmos, from reverence and imagination to exploration and discovery. As we study Venus with new technologies and missions, we carry with us not just the tools of science, but also the echoes of the myths and stories that have shaped our fascination with the planet for millennia. The scientific understanding of Venus began with curiosity and wonder. For centuries, its brightness and phases, visible even to the naked eye, set it apart as one of the most intriguing objects in the sky. But, as telescopes advanced, so did humanity's ambition to uncover the secrets of this enigmatic planet. In 1610, Galileo Galilei pointed his telescope toward Venus and made a groundbreaking observation. He discovered that Venus exhibited phases similar to those of the Moon, cycling from crescent to full and back again. This provided crucial evidence that Venus orbited the Sun, not Earth, supporting the then controversial heliocentric model proposed by Copernicus. It was a pivotal moment, not just for Venus, but for the understanding of our entire solar system. Later, in 1761, the rare event known as the transit of Venus offered another opportunity for discovery. During a transit, Venus passes directly between the Earth and the Sun, appearing as a small black dot moving across the Sun's glowing face. Russian scientist Mikhail Lomonosov, observing this phenomenon, noticed a faint halo of light surrounding Venus, revelation that would shape scientific curiosity for centuries. By the 19th century, astronomers were eager to understand what lay beneath Venus's mysterious clouds. Many believed that the planet's dense atmosphere was composed of water vapor, and that its surface harbored oceans and rainforests, much like Earth's tropical regions. These assumptions sparked widespread speculation, leading to romanticized depictions of Venus in both scientific literature and fiction. In the early 20th century, as science fiction flourished, writers imagined Venus as a lush world filled with life. Novels and stories described Venus as a planet of endless jungles, prehistoric creatures, and untamed beauty. For a time, Venus was seen as a potential second Earth, a place of adventure and possibility. But these dreams began to unravel as technology advanced and the first missions to Venus brought back sobering truths. The era of space exploration began in earnest in the mid-20th century, and Venus was one of the first targets. NASA's Mariner 2, launched in 1962, was the first spacecraft to successfully conduct a flyby of another planet. Its instruments revealed that Venus's surface temperature was far hotter than anticipated, reaching nearly 475 degrees Celsius. This discovery shattered the idea of Venus as a habitable world and marked the beginning of a new understanding of its extreme conditions. The Soviet Union took an even bolder approach with its Venera program, a series of missions that aimed to land on Venus's surface. The early attempts were met with challenges, as spacecraft succumbed to the planet's crushing pressures and scorching temperatures. But by 1970, the Soviets achieved a monumental breakthrough. Venera 7 became the first spacecraft to successfully land on another planet and transmit data back to Earth. It survived for just 23 minutes, but its achievement paved the way for further exploration. In subsequent missions, the Venera landers sent back the first images of Venus's surface. These grainy black and white photos revealed a desolate, rocky terrain, unlike the imagined jungles of earlier speculation. The landers also measured the planet's atmospheric composition, confirming the dominance of carbon dioxide and the presence of sulfuric acid in the clouds. Meanwhile, NASA continued its exploration of Venus with orbital missions. In 1978, the Pioneer Venus orbiter conducted detailed studies of the planet's atmosphere, mapping its composition and structure. It was followed by the Magellan mission in the 1990s, which used radar to penetrate the thick clouds and map 97% of Venus's surface. Magellan's radar images revealed a world dominated by volcanic features, vast lava plains, and strange tessellated highlands. These missions fundamentally transformed humanity's view of Venus. What was once thought to be a tropical paradise was revealed as a hostile alien world. The discoveries raised new questions about Venus's past. How could a planet that may have once harbored oceans and a temperate climate transform into such an inferno? What forces caused its atmosphere to become so thick and its surface so volcanic? Despite the challenges, Venus remains a compelling target for exploration. Its proximity to Earth and its striking similarities in size and composition make it a natural laboratory for studying planetary evolution. Missions to Venus have also tested the limits of engineering, pushing scientists to develop new technologies capable of withstanding the planet's extreme conditions. The journey to understand Venus is far from over. New missions are being planned by space agencies worldwide, including NASA's Veritas and Da Vinci Plus missions, and the European Space Agency's Envision orbiter. These missions aim to study Venus's surface and atmosphere in greater detail, searching for clues about its ancient past and the processes that shaped its present. Venus's exploration has been a story of persistence and discovery, filled with triumphs and challenges. It is a reminder of humanity's unyielding desire to understand the unknown and our ability to adapt and innovate in the face of seemingly insurmountable obstacles. Each new mission brings us closer to unraveling the mysteries of this enigmatic planet, shedding light not only on Venus, but also on the forces that govern the evolution of all worlds. Billions of years ago, Venus and Earth shared a striking resemblance. Both planets were formed from the same cosmic materials, orbiting in the Sun's habitable zone, and were likely equipped with the ingredients for sustaining life. Venus, the slightly closer sibling, may have been blanketed by shallow oceans, its atmosphere filled with water vapor and other life-supporting gases. For a time, Venus may have been a kindred planet, a mirror image of Earth in its earliest days. Scientific studies suggest that Venus's surface once hosted liquid water, possibly enough to cover the planet in oceans tens of meters deep. With an atmosphere likely similar to early Earth's, Venus may have experienced a stable climate where water played a central role in shaping its surface. In this ancient world, volcanic activity would have interacted with the atmosphere, cycling gases in a process that helped regulate temperatures. Rivers might have carved valleys, and the interaction between water and rock could have created environments suitable for the formation of life. But this promising beginning did not last. Venus began to change, and the forces that governed its fate diverged sharply from those shaping Earth. One of the most compelling pieces of evidence for Venus's watery past lies in its tessera terrains. These elevated, intricately patterned regions may hold the geological fingerprints of ancient oceans. Tesserae are thought to be among the oldest surfaces on Venus, dating back billions of years, and their composition suggests they may have formed in the presence of water. The loss of Venus's water marked the turning point in its transformation. As its proximity to the sun caused temperatures to rise, more water evaporated from the planet's surface, releasing water vapor into the atmosphere. Water vapor, a potent greenhouse gas, trapped heat and drove temperatures even higher. This created a feedback loop, a runaway greenhouse effect that caused Venus's oceans to boil away completely. Without oceans, Venus lost its ability to regulate carbon dioxide levels. On Earth, oceans play a critical role in the carbon cycle, absorbing carbon dioxide from the atmosphere and storing it in rocks and sediments. But as Venus's water disappeared, this natural process ceased, allowing carbon dioxide to build up unchecked. Volcanic eruptions continue to release more carbon dioxide into the atmosphere, intensifying the greenhouse effect and transforming Venus into the inferno it is today. Another key factor in Venus's evolution was the lack of a magnetic field. Unlike Earth, Venus does not have the protective shield of a magnetic field to deflect the solar wind, a constant stream of charged particles from the sun. Over time, this relentless bombardment stripped Venus of its remaining hydrogen, a critical component of water, and left the planet dry and barren. What remains of Venus's early history is difficult to discern, as the planet's surface has been reshaped by volcanic activity. Most of Venus's crust is relatively young, with its current landscape dating back only about 500 million years. This means that much of its ancient geological record has been erased, complicating efforts to reconstruct its past. However, scientists believe that the tessera terrains, being the oldest regions, may still hold clues about Venus's primeval conditions. Despite these challenges, the possibility that Venus was once habitable raises profound questions. If Venus and Earth started with such similar conditions, why did they evolve so differently? Could life have arisen on Venus during its early Earth-like phase? And if so, did it perish as the planet became increasingly hostile? Or could it have found a way to survive in the upper atmosphere, where conditions remained relatively temperate? The idea that Venus might have supported life billions of years ago is not as far-fetched as it once seemed. On Earth, life began quickly, appearing within a few 100 million years after the planet's formation. If similar conditions existed on Venus, there is every reason to believe that life could have emerged there as well. However, the loss of water and the onset of extreme temperatures likely extinguished any chance for life to thrive on the surface. For scientists, unraveling the mystery of Venus's past is about more than understanding one planet's history. It is about learning why Earth succeeded where Venus failed. The two planets began with such promise, but small differences in their positions, compositions, or geological processes may have led to vastly different outcomes. By studying Venus, researchers hope to identify the critical factors that make a planet habitable and protect it from catastrophic change. The implications extend far beyond our solar system. Thousands of exoplanets have already been discovered, and many are Earth-sized worlds orbiting within their stars' habitable zones. Yet, Venus reminds us that size and location alone are not enough to determine a planet's potential for life. Understanding the processes that turned Venus into a furnace will help scientists interpret the conditions of distant worlds and refine the search for truly habitable planets. Venus's past also serves as a cautionary tale for Earth. It highlights the fragility of planetary systems and the consequences of disrupting the delicate balance between climate, atmosphere, and geology. By studying Venus, we gain not only a glimpse into the distant past, but also a warning about the potential challenges that lie ahead for our own planet. In the story of Venus, we see the possibilities of what might have been and the stark realities of what came to pass. It is a tale of transformation, a reminder that even the most promising worlds can succumb to forces beyond their control. Yet within this tale lies hope, as the lessons of Venus guide us in protecting the fragile balance that sustains life on Earth. At first glance, Venus and Earth appear to be celestial twins. They are nearly identical in size, with Venus being only slightly smaller. Their compositions are remarkably similar, both formed from the same primordial materials. Yet their fates could not be more different. While Earth evolved into a thriving, life-sustaining world, Venus became an uninhabitable furnace. Understanding the key differences between these two planets is central to unraveling the mysteries of planetary evolution. One of the most fundamental differences lies in their positions relative to the Sun. Venus orbits closer, receiving nearly twice as much solar energy as Earth. This proximity intensified the greenhouse effect early in Venus's history, gradually heating the planet and evaporating its oceans. Without water to regulate the climate and absorb carbon dioxide, Venus's atmospheric temperatures began to soar. Earth, in contrast, sits in the middle of the Sun's habitable zone, where liquid water can persist on the surface. This delicate positioning allowed Earth's climate to stabilize, creating conditions suitable for the emergence of life. Venus's slightly closer orbit, while seemingly a small difference, set the stage for a runaway greenhouse effect and would seal its fate. Another critical distinction is Venus's lack of a magnetic field. On Earth, the magnetic field acts as a protective shield, deflecting the Sun's charged particles and preserving the atmosphere. This field is generated by the motion of molten iron in Earth's core, a process known as the dynamo effect. Venus, however, lacks such protection. The planet's slow rotation, one day on Venus lasts longer than its year, may have prevented the dynamo effect from operating efficiently. Without a magnetic field, Venus's atmosphere was left vulnerable to the relentless bombardment of the solar wind. Over time, this stripped away lighter elements, such as hydrogen, which are critical for forming and retaining water. The differences in geological activity between the two planets also played a pivotal role in their divergent fates. On Earth, plate tectonics constantly renew the surface, recycling carbon dioxide through a natural process. When volcanoes erupt, they release carbon dioxide into the atmosphere, but over time this gas is absorbed by the oceans and stored in rocks. This cycling of carbon helps regulate Earth's climate, preventing extreme temperature swings. Venus, on the other hand, does not appear to have plate tectonics. Its crust is much thicker than Earth's, forming a rigid lid that prevents the surface from breaking into plates. This lack of movement has significant consequences. Without subduction zones, regions where one tectonic plate dives beneath another, Venus cannot recycle carbon dioxide into its crust. Instead, the gas accumulates in the atmosphere, intensifying the greenhouse effect and trapping heat. Despite the absence of plate tectonics, Venus is not geologically inactive. The planet's surface is dominated by vast volcanic plains, shield volcanoes, and other volcanic features. However, instead of releasing heat gradually, as Earth does, Venus appears to experience episodic bursts of volcanic activity. These cataclysmic events may have resurfaced the entire planet roughly 500 million years ago, erasing most evidence of its earlier history. Another key difference lies in the atmospheric compositions of Venus and Earth. Venus's atmosphere is overwhelmingly carbon dioxide, with clouds of sulfuric acid, while Earth's atmosphere contains a balanced mixture of nitrogen, oxygen, and trace gases. Water vapor, crucial for life, is almost entirely absent from Venus's atmosphere, a stark contrast to Earth's abundant supply. The differences in atmospheric pressure are equally dramatic. Venus's atmosphere is nearly 90 times denser than Earth's, exerting a crushing force on anything that lands on its surface. This dense air traps heat through the greenhouse effect, creating a surface temperature hotter than that of Mercury, despite Venus being farther from the Sun. Interestingly, Venus and Earth share similar internal structures, including a molten iron core and a rocky mantle, yet Venus's thick crust and stagnant geology prevent the dynamic processes that characterize Earth's interior. This rigidity limits Venus's ability to release heat, causing volcanic activity to build pressure over time and erupt catastrophically. These distinctions between Venus and Earth highlight the delicate balance required to sustain a habitable planet. While the two worlds began with comparable conditions, small differences in orbit, rotation, geology, and magnetic fields led to dramatically different outcomes. Venus's story underscores how a few critical factors can tip the scales between habitability and desolation. For scientists, comparing Venus and Earth provides valuable insights into planetary evolution. It helps refine models of how atmospheres, climates, and geologies interact over billions of years. Venus, as Earth's evil twin, serves as a laboratory for understanding what could have gone wrong on our planet, and what might still go wrong if key systems fail. These lessons extend far beyond the solar system. Thousands of Earth-sized exoplanets have been discovered orbiting distant stars, many in positions that suggest they could support liquid water. But, as Venus demonstrates, size and distance from a star are only part of the equation. A planet's ability to maintain balance through its atmosphere, geology, and magnetic field is just as important. Studying the key differences between Venus and Earth is not merely an exercise in understanding the past. It is a glimpse into the fragility of planetary systems and a reminder of the forces that shape worlds into oases of life or barren, lifeless landscapes. Venus's fate is a cautionary tale for any planet, including our own, and a testament to the complexity of what makes a world truly habitable. Venus, once a potential Earth-like paradise, underwent one of the most catastrophic climate transformations in the solar system. What began as a planet with conditions that may have supported liquid water devolved into a blistering wasteland dominated by a runaway greenhouse effect. Understanding how Venus descended into this state is crucial for unraveling its past and offers a stark warning for Earth's future. The story begins with Venus's position in the solar system. Receiving nearly twice the solar radiation of Earth, Venus experienced higher surface temperatures early in its history. Despite this, its early climate may have been stabilized by the presence of oceans that helped regulate atmospheric temperatures, similar to Earth's carbon cycle. These oceans absorbed carbon dioxide from the atmosphere and stored it in rocks, creating a balance that could have lasted for hundreds of millions of years. But this equilibrium was not to last. As the sun's brightness gradually increased, more heat reached Venus's surface, causing water from its oceans to evaporate. Water vapor, a potent greenhouse gas, accumulated in the atmosphere, trapping even more heat. This initiated a feedback loop, the runaway greenhouse effect, that drove temperatures higher and higher. As the oceans evaporated completely, Venus lost one of its most critical climate regulators. On Earth, the carbon cycle plays a vital role in stabilizing temperatures. Carbon dioxide released by volcanoes is absorbed by water, where it reacts with minerals to form carbonate rocks, effectively removing it from the atmosphere. But with no water left on Venus, this process ceased. Carbon dioxide released by volcanic activity built up in the atmosphere, amplifying the greenhouse effect and turning Venus into a furnace. The planet's lack of a magnetic field further exacerbated its fate. Without this protective shield, the solar wind, a stream of charged particles from the sun, was able to strip away lighter elements, such as hydrogen, from Venus's upper atmosphere. This process, called atmospheric escape, robbed Venus of the hydrogen needed to form water, permanently drying out the planet. Today, Venus's atmosphere is a stark testament to this climatic collapse. Composed of 96.5% carbon dioxide, it exerts a surface pressure 90 times greater than Earth's. Temperatures average a blistering 475 degrees Celsius, hot enough to melt lead. Sulfur dioxide, another greenhouse gas, is also abundant, contributing to the planet's acidic clouds. These clouds reflect sunlight, giving Venus its brilliant appearance from afar, but they also trap heat, creating an insulating effect that prevents any cooling of the surface. The result is a planet locked in a vicious cycle of heat and pressure. The atmosphere's density ensures that any heat reaching the surface is trapped, making Venus the hottest planet in the solar system, despite being farther from the Sun than Mercury. One of the most striking differences between Venus and Earth is the absence of plate tectonics on Venus. On Earth, the movement of tectonic plates helps regulate the climate by recycling carbon dioxide. When tectonic plates collide, one can sink beneath the other in a process called subduction, carrying carbon-rich rocks into the mantle. There, the carbon is released back into the atmosphere through volcanic eruptions, completing the carbon cycle. Venus's thick, rigid crust prevents this process. Instead of plate tectonics, Venus appears to undergo episodic resurfacing events, where volcanic activity periodically releases vast amounts of heat and gas. These events, which may cover the planet in fresh lava, contribute to the accumulation of carbon dioxide in the atmosphere and the planet's inability to cool over time. The planet's surface, shaped by this relentless volcanism, reflects the consequences of this runaway process. Lava flows, shield volcanoes, and strange fractured terrains dominate the landscape, serving as a reminder of the immense geological forces at play. These features, preserved under the unchanging atmosphere, are a record of Venus's fiery transformation. Despite its extreme conditions, Venus holds valuable lessons for understanding climate change, not just on other planets, but here on Earth. The runaway greenhouse effect that overtook Venus offers a glimpse into what could happen if a planet loses its ability to regulate atmospheric carbon dioxide. While Earth's climate is stabilized by the interplay of oceans, atmosphere, and plate tectonics, disruptions to this balance could have dire consequences. For scientists, Venus is a cautionary tale of how planetary systems can spiral out of control. It demonstrates the interconnectedness of geology, atmosphere, and climate, showing how the failure of one system can lead to catastrophic changes. Venus's transformation also underscores the importance of water in maintaining planetary habitability. Without it, even the most promising worlds can succumb to environmental collapse. Studying Venus's greenhouse effect is about more than understanding its past. It is a way to safeguard Earth's future. By examining the processes that led to Venus's climatic death, scientists hope to better understand the potential tipping points in Earth's climate system and how to avoid them. Venus serves as a reminder of the delicate balance required to sustain life and the consequences of losing that balance. Venus's fate is a stark warning, but it is also a source of knowledge. By unraveling the mysteries of its atmospheric evolution, scientists are gaining insights into the forces that shape planets and their climates. This knowledge is crucial not only for Earth, but also for interpreting the conditions of distant exoplanets, where the line between habitability and hostility may be just as fine. As we continue to study Venus, it remains both a cautionary tale and a scientific treasure. Its searing surface and thick, choking atmosphere tell a story of what can go wrong, but they also offer hope. Hope that through understanding we can protect the fragile balance that sustains life on Earth and recognize the warning signs on other worlds before it is too late. The atmosphere of Venus is one of the most extreme and enigmatic features of the planet. Thick, dense, and opaque, it conceals the surface from direct observation and creates an environment unlike any other in the solar system. While the atmosphere poses immense challenges for exploration, it also holds tantalizing clues to Venus's past and potential future. Venus's atmosphere is dominated by carbon dioxide, which makes up 96.5% of its composition. This high concentration of greenhouse gas is the primary driver of the planet's extreme surface temperatures, which average around 475 degrees Celsius. Traces of nitrogen and sulfur dioxide contribute to the thick, choking air, while clouds of sulfuric acid create an impenetrable veil over the planet. These clouds, highly reflective, give Venus its dazzling brilliance when viewed from Earth, masking the hostile environment below. One of the most striking features of Venus's atmosphere is its density. At the surface, the pressure is 90 times that of Earth's, equivalent to being nearly a kilometer underwater. This immense pressure has proven to be one of the greatest obstacles to exploration, as even the most robust spacecraft struggle to survive for more than a few hours under these conditions. Despite its oppressive nature, the Venusian atmosphere has an intricate structure. It is divided into several layers, each with distinct properties. At higher altitudes, the temperature and pressure drop significantly, creating a region where conditions are surprisingly Earth-like. Around 50 kilometers above the surface, the atmosphere's temperature and pressure resemble those found at sea level on Earth. This layer, known as the habitable zone of Venus's atmosphere, has sparked interest in its potential to support microbial life or future human exploration. The clouds of Venus, however, are a double-edged sword. Composed primarily of sulfuric acid droplets, they create a highly corrosive environment that poses challenges for both robotic and human missions. Lightning frequently illuminates these clouds, accompanied by powerful winds that drive a phenomenon called superrotation. In this process, the atmosphere circles the planet at speeds of up to 360 kilometers per hour, completing a rotation in just 4 Earth days, much faster than the planet itself rotates. One of the most mysterious aspects of Venus's atmosphere is the presence of ultraviolet and UV absorption anomalies. Observations from Earth-based telescopes and space missions have revealed dark patches in the clouds that absorb UV light. These patches, made of an unknown substance, have puzzled scientists for decades. Some researchers speculate that they could be a result of unusual chemical reactions, while others suggest a more intriguing possibility: the presence of microbial life. The idea of life in Venus's atmosphere is not as far-fetched as it might seem. On Earth, microorganisms have been found thriving in extreme environments, including acidic hot springs, radioactive waste, and even the upper layers of our own atmosphere. The habitable zone in Venus's clouds offers a region with temperatures and pressures that could, in theory, support life. While the highly acidic environment presents a significant barrier, some Earth microbes known as extremophiles are capable of surviving in similar conditions. The discovery of phosphine gas in Venus's atmosphere in 2020 further fueled speculation about potential life. Phosphine is a molecule associated with biological processes on Earth, and its detection in Venus's upper clouds sparked intense debate. While some scientists argued that the presence of phosphine could indicate microbial life, others suggested non-biological explanations, such as volcanic activity or chemical reactions. The question remains unresolved, highlighting the need for more detailed atmospheric studies. Exploring Venus's atmosphere presents unique opportunities for scientific advancement. Unlike the surface, where extreme temperatures and pressures limit mission lifespans, the upper atmosphere offers a more forgiving environment for exploration. Concepts such as balloon-based probes, aerial drones, and even floating research stations have been proposed to study the atmospheric layers in detail. These platforms could collect data on temperature, pressure, chemical composition, and cloud dynamics while avoiding the challenges of landing on the surface. One of the most ambitious proposals is the High-Altitude Venus Operational Concept, or HABIC. This concept envisions large, helium-filled airships floating in Venus's upper atmosphere, where conditions are similar to those on Earth. These airships could host scientific instruments to study the clouds, atmosphere, and potential signs of life, while also serving as test beds for future human exploration. Venus's atmosphere also holds valuable clues about the planet's history. By analyzing its isotopic composition, scientists can piece together the story of how Venus lost its water. Noble gases like argon, krypton, and xenon, which are present in trace amounts, act as fossils of the planet's early atmosphere. Their ratios provide insight into processes such as volcanic outgassing, atmospheric escape, and the loss of hydrogen over billions of years. The interactions between Venus's atmosphere and its surface are another critical area of study. The intense heat and pressure at the surface cause chemical reactions that release gases into the atmosphere, while volcanic eruptions may inject sulfur dioxide and other compounds into the clouds. Understanding these processes is essential for reconstructing Venus's climatic evolution and its shift from a potentially habitable world to an inhospitable world. As we continue to explore Venus, its atmosphere serves as both a barrier and a beacon. It challenges the limits of technology and imagination while offering unparalleled opportunities for discovery. Studying Venus's atmosphere could unlock the secrets of its past, shed light on the processes that shape planetary climates, and even offer clues about the potential for life in the most unexpected places. The mysteries of Venus's atmosphere remind us of the complexity and diversity of planetary systems. From its swirling clouds to its turbulent winds, the atmosphere of Venus is a world unto itself, ripe for exploration. With each new mission, we take another step closer to understanding this enigmatic planet and the lessons it holds for Earth, our solar system, and the universe beyond. The atmosphere of Venus is one of the most extreme and enigmatic features of the planet. Thick, dense, and opaque, it conceals the surface from direct observation and creates an environment unlike any other in the solar system. While the atmosphere poses immense challenges for exploration, it also holds tantalizing clues to Venus's past and potential future. Venus's atmosphere is dominated by carbon dioxide, which makes up 96.5% of its composition. This high concentration of greenhouse gas is the primary driver of the planet's extreme surface temperatures, which average around 475 degrees Celsius. Traces of nitrogen and sulfur dioxide contribute to the thick, choking air, while clouds of sulfuric acid create an impenetrable veil over the planet. These clouds, highly reflective, give Venus its dazzling brilliance when viewed from Earth, masking the hostile environment below. Clouds disappearing, separating the formation's terror-fixated lover to hide from. One of the most striking features of Venus's atmosphere is its density. At the surface, the pressure is 90 times that of Earth's, equivalent to being nearly a kilometer underwater. This immense pressure has proven to be one of the greatest obstacles to exploration, as even the most robust spacecraft struggle to survive for more than a few hours under these conditions. Despite its oppressive nature, the Venusian atmosphere has an intricate structure. It is divided into several layers, each with distinct properties. At higher altitudes, the temperature and pressure drop significantly, creating a region where conditions are surprisingly Earth-like. Around 50 kilometers above the surface, the atmosphere's temperature and pressure resemble those found at sea level on Earth. This layer, known as the habitable zone of Venus's atmosphere, has sparked interest in its potential to support microbial life or future human exploration. The clouds of Venus, however, are a double-edged sword. Composed primarily of sulfuric acid droplets, they create a highly corrosive environment that poses challenges for both robotic and human missions. Lightning frequently illuminates these clouds, accompanied by powerful winds that drive a phenomenon called superrotation. In this process, the atmosphere circles the planet at speeds of up to 360 kilometers per hour, completing a rotation in just 4 Earth days, much faster than the planet itself rotates. One of the most mysterious aspects of Venus's atmosphere is the presence of ultraviolet UV absorption anomalies. Observations from Earth-based telescopes and space missions have revealed dark patches in the clouds that absorb UV light. These patches, made of an unknown substance, have puzzled scientists for decades. Some researchers speculate that they could be a result of unusual chemical reactions, while others suggest a more intriguing possibility: the presence of microbial life. The idea of life in Venus's atmosphere is not as far-fetched as it might seem. On Earth, microorganisms have been found thriving in extreme environments, including acidic hot springs, radioactive waste, and even the upper layers of our own atmosphere. The habitable zone in Venus's clouds offers a region with temperatures and pressures that could, in theory, support life. While the highly acidic environment presents a significant barrier, some Earth microbes, known as extremophiles, are capable of surviving in similar conditions. The discovery of phosphine gas in Venus's atmosphere in 2020 further fueled speculation about potential life. Phosphine is a molecule associated with biological processes on Earth, and its detection in Venus's upper clouds sparked intense debate. While some scientists argued that the presence of phosphine could indicate microbial life, others suggested non-biological explanations, such as volcanic activity or chemical reactions. The question remains unresolved, highlighting the need for more detailed atmospheric studies. Exploring Venus's atmosphere presents unique opportunities for scientific advancement. Unlike the surface, where extreme temperatures and pressures limit mission lifespans, the upper atmosphere offers a more forgiving environment for exploration. Concepts such as balloon-based probes, aerial drones, and even floating research stations have been proposed to study the atmospheric layers in detail. These platforms could collect data on temperature, pressure, chemical composition, and cloud dynamics, while avoiding the challenges of landing on the surface. One of the most ambitious proposals is the High-Altitude Venus Operational Concept, or HAVOC. This concept envisions large, helium-filled airships floating in Venus's upper atmosphere, where conditions are similar to those on Earth. These airships could host scientific instruments to study the clouds, atmosphere, and potential signs of life, while also serving as test beds for future human exploration. Venus's atmosphere also holds valuable clues about the planet's history. By analyzing its isotopic composition, scientists can piece together the story of how Venus lost its water. Noble gases like argon, krypton, and xenon, which are present in trace amounts, act as fossils of the planet's early atmosphere. Their ratios provide insight into processes such as volcanic outgassing, atmospheric escape, and the loss of hydrogen over billions of years. The interactions between Venus's atmosphere and its surface are another critical area of study. The intense heat and pressure at the surface cause chemical reactions that release gases into the atmosphere, while volcanic eruptions may inject sulfur dioxide and other compounds into the clouds. Understanding these processes is essential for reconstructing Venus's climatic evolution and its shift from a potentially habitable world to an inhospitable world. As we continue to explore Venus, its atmosphere serves as both a barrier and a beacon. It challenges the limits of technology and imagination, while offering unparalleled opportunities for discovery. Studying Venus's atmosphere could unlock the secrets of its past, shed light on the processes that shape planetary climates, and even offer clues about the potential for life in the most unexpected places. The mysteries of Venus's atmosphere remind us of the complexity and diversity of planetary systems. From its swirling clouds to its turbulent winds, the atmosphere of Venus is a world unto itself, ripe for exploration. With each new mission, we take another step closer to understanding this enigmatic planet and the lessons it holds for Earth, our solar system, and the universe beyond. Exploring Venus is one of the greatest challenges in planetary science. Its extreme surface conditions, blistering heat, crushing pressure, and corrosive clouds have defeated even the most robust spacecraft. Yet Venus is also a treasure trove of scientific discovery, holding answers to fundamental questions about planetary evolution, climate systems, and the potential for life. To unlock its secrets, scientists and engineers have developed innovative ideas to overcome the planet's formidable barriers. One of the most promising approaches focuses on Venus's atmosphere rather than its surface. Roughly 50 kilometers above the ground, the pressure and temperature resemble conditions at sea level on Earth. This region, known as Venus's visible zone, offers a more hospitable environment for exploration. Here, atmospheric probes, balloons, and even floating research stations could operate for extended periods, gathering data about the clouds, winds, and atmospheric chemistry. A key concept for atmospheric exploration is the deployment of balloon-based missions. The Soviet Union pioneered this approach in 1985 with the Vega 1 and Vega 2 probes, which carried helium-filled balloons into Venus's atmosphere. These balloons drifted with the winds for several days, collecting data on temperature, pressure, and cloud composition. Despite their brief lifespans, they demonstrated the feasibility of atmospheric exploration and paved the way for more advanced missions. Building on this foundation, NASA and other space agencies have proposed a variety of modern balloon-based concepts. Equipped with advanced sensors, cameras, and communication systems, these platforms could float through the habitable zone, providing continuous monitoring of Venus's dynamic atmosphere. Some designs include solar-powered balloons that could adjust their altitude, allowing them to sample different atmospheric layers and study the planet's cloud structure in unprecedented detail. One of the most ambitious ideas is the High-Altitude Venus Operational Concept, or HAVOC. This futuristic vision involves deploying massive helium-filled airships capable of carrying scientific payloads or even human crews. Floating high above Venus's hostile surface, these airships could serve as mobile laboratories, conducting experiments and deploying smaller probes. Powered by solar panels, they would use the abundant sunlight above the cloud layer to maintain operations for months or even years. The concept of a Venus cloud city may sound like science fiction, but it represents a bold step forward in exploration. Scientists and engineers have envisioned permanent research stations suspended in Venus's atmosphere, where conditions are stable enough to support long-term missions. These floating habitats could be constructed using lightweight materials, such as carbon fiber, and designed to withstand the acidic environment. In addition to studying Venus, these habitats could serve as prototypes for similar installations on other planets with thick atmospheres. Surface exploration remains one of the most challenging yet enticing aspects of Venus missions. To survive the planet's extreme heat and pressure, spacecraft must be built with cutting-edge materials and innovative designs. The Soviet Union's Venera landers, which operated for just minutes or hours on Venus's surface, provided a glimpse of what is possible. Today, engineers are developing new technologies that could extend the lifespan of humans on Venus. One such breakthrough involves the development of high-temperature electronics. Traditional circuits fail at temperatures above 125 degrees Celsius. But new materials, such as silicon carbide, can operate at much higher temperatures. These advancements could enable landers to function on Venus's surface for weeks or even months, dramatically increasing the amount of data they can collect. Another intriguing concept is the design of wind-powered rovers. Venus's dense atmosphere produces slow but powerful winds that could be harnessed to propel mechanical rovers across the surface. These rovers would rely on turbines to capture wind energy, eliminating the need for solar panels, which are less effective beneath Venus's thick clouds. By using gears and springs instead of delicate electronics, these wind-powered vehicles can operate in Venus's harsh conditions for extended periods. For missions that aim to study both the surface and atmosphere, hybrid platforms could provide a versatile solution. Probes could descend through the atmosphere, collecting data as they fall, before deploying landers to the surface. Some designs even include deployable balloons that could ascend back into the atmosphere after completing their surface missions, carrying valuable samples and data to orbiting spacecraft for analysis. Orbiters also play a crucial role in Venus exploration, offering a bird's-eye view of the planet. Radar-equipped orbiters, such as NASA's planned Veritas mission and the European Space Agency's Envision mission, will map Venus's surface in high resolution, revealing details about its geology and tectonic activity. These missions will also study the interaction between Venus's surface and atmosphere, providing new insights into the planet's climatic history. Beyond traditional approaches, scientists are exploring ways to extract resources directly from Venus's atmosphere. The dense carbon dioxide atmosphere offers potential for in-situ resource utilization, ESRU, where atmospheric gases could be harvested and converted into materials or fuel. For example, carbon dioxide could be used to produce oxygen for life support, or carbon-based materials for construction. Such technologies could revolutionize long-term exploration, reducing the need to transport supplies from Earth. Venus's extreme environment has also inspired research into new propulsion and communication technologies. Solar-powered aircraft capable of flying in Venus's upper atmosphere are being developed, offering an alternative to balloons and orbiters. Meanwhile, high-temperature resistant communication systems are being designed to maintain contact with landers and transmit data from the surface. Despite the immense challenges, the allure of Venus remains strong. Each new mission concept represents a step closer to understanding this enigmatic planet and unlocking its secrets. From floating cities in the clouds to resilient rovers on the surface, the innovative ideas for exploring Venus showcase the ingenuity and determination of humanity's quest for knowledge. As scientists and engineers continue to push the boundaries of what is possible, Venus serves as both a test-bed for cutting-edge technologies and a reminder of the complexity of planetary exploration. With each new innovation, we edge closer to uncovering the mysteries of our closest planetary neighbor and gaining insights that could transform our understanding of the universe. Venus and Earth, once so similar in their early days, offer a striking example of how two planets can diverge so profoundly. This duality has become a cornerstone for understanding not only our own solar system, but also the thousands of exoplanets being discovered around distant stars. As scientists study Venus and Earth side by side, they uncover critical insights into planetary evolution, the potential for habitability, and the delicate factors that determine a world's fate. The study of exoplanets has surged in recent decades, with over 5,000 confirmed planets orbiting stars beyond our Sun. Many of these are Earth-sized and exist in what astronomers call the habitable zone, a region around a star where temperatures might allow liquid water to exist on the surface. This range of distances has long been considered the most likely place for life to emerge, but Venus challenges this assumption. Venus sits just outside the inner edge of our solar system's habitable zone, yet evidence suggests it may have once harbored oceans and a temperate climate. What changed? By studying Venus's transformation, scientists can better understand the fine line between habitability and desolation. One of the key lessons from Venus is that proximity to a star is only one piece of the puzzle. While Venus is closer to the Sun than Earth, its distance alone does not explain its extreme conditions. The runaway greenhouse effect, driven by its thick atmosphere and loss of water, played a far more significant role. This means that exoplanets within the habitable zone may not be habitable at all if they have Venus-like atmospheric conditions. Astronomers are beginning to apply this Venusian lens to the study of exoplanets. The discovery of so-called Venus analogs among exoplanets, worlds that are Earth-sized but swathed in thick, hot atmospheres. These findings underscore the importance of studying atmospheric composition and dynamics alongside a planet's size and distance from its star. Venus's lack of a magnetic field also offers a cautionary tale for exoplanets. Without this protective shield, solar winds can strip away an atmosphere over time, as they did on Venus. This vulnerability can make otherwise Earth-like planets uninhabitable, even if they are in the right orbit. When scientists search for potentially habitable worlds, the presence of a magnetic field may become a critical factor in determining their suitability for life. The search for Earth-like worlds is further complicated by the wide variety of planetary systems observed in the galaxy. Many stars have planets that orbit much closer than Mercury does to the Sun, suggesting that Venus-like conditions might be more common than previously thought. These close-in planets, often subjected to intense stellar radiation, may resemble Venus more than Earth, regardless of their initial potential for habitability. In some ways, Venus expands the definition of what astronomers consider the habitable zone. If Venus once had oceans and a temperate climate, then the habitable zone for a young star might extend closer than previously assumed. Conversely, planets farther out in the habitable zone might also experience runaway greenhouse effects under the right conditions. Venus reminds us that habitability is not a static property, but a dynamic state influenced by a planet's atmosphere, geology, and relationship to its star over time. One of the most exciting developments in exoplanet science is the capability to study planetary atmospheres directly. Instruments like the James Webb Space Telescope, JWST, are beginning to analyze the light passing through exoplanetary atmospheres, searching for signs of water vapor, carbon dioxide, and other molecules. By comparing these findings with what we know about Venus and Earth, scientists can better interpret the conditions on distant worlds. For example, detecting a high concentration of carbon dioxide in an exoplanet's atmosphere might indicate a runaway greenhouse state, making it more Venus-like than Earth-like. Venus also forces scientists to confront deeper philosophical questions about life in the universe. If two planets so similar in size, composition, and origin could end up so differently, how common is this divergence? Is life a rare fluke, dependent on an extraordinary alignment of factors, or is it an inevitable outcome on worlds like Earth? The contrasting fates of Venus and Earth suggest that habitable conditions may be more fragile and fleeting than previously thought. Yet Venus's story is not purely one of caution. It also highlights the resilience of planetary systems. Despite its hostile environment today, Venus's past may have been one of promise, with conditions ripe for the emergence of life. Understanding how long Venus remained habitable and why it eventually lost that potential could reveal vital clues about the longevity of life-supporting environments elsewhere in the galaxy. The exploration of Venus is thus intimately tied to the study of exoplanets. By piecing together the history of our closest planetary neighbor, scientists refine their models for distant worlds. Venus serves as a reminder that the search for life is as much about what makes a planet uninhabitable as it is about what makes it a haven for life. As the field of exoplanet research advances, Venus will continue to play a pivotal role. Its lessons, born of extremes, offer a guide to interpreting the data from far-off worlds. With each new discovery, we gain a deeper understanding of the forces that shape planetary destinies and a clearer picture of where life might exist among the stars. For decades, Venus was overlooked in the rush to explore Mars and the outer planets. Mars, with its cold deserts and signs of ancient rivers, captured the imagination as a potential haven for past or even present life. Meanwhile, the gas giants and their moons, with their subsurface oceans and dynamic atmospheres, offered tantalizing possibilities for exploration. Venus, by comparison, seemed like a closed book, a hostile, unyielding world where little could be learned. Yet, Venus is far from irrelevant. It is a planetary laboratory, filled with lessons about climate, geology, and the fragile balance that determines a planet's habitability. In recent years, the scientific community has reignited its interest in Venus, recognizing its critical role in understanding both our solar system and exoplanets throughout the galaxy. One of Venus's greatest contributions is its value as Earth's closest planetary sibling. As nearly identical twins in size, mass, and composition, Venus and Earth started their journeys with remarkable similarities. By studying why their paths diverged so drastically, scientists gain insight into the forces that shape a planet's destiny. Venus represents an alternative history of Earth, a stark vision of what could have happened had conditions on our planet spiraled out of control. Venus also provides an unparalleled opportunity to study the greenhouse effect on a global scale. While Earth experiences a regulated greenhouse effect, where carbon dioxide and water vapor trap just enough heat to sustain life, Venus demonstrates what happens when this system breaks down. Its atmosphere, thick with carbon dioxide, traps immense amounts of solar energy, driving surface temperatures to uninhabitable extremes. Understanding how this runaway effect occurred on Venus could help scientists refine climate models for Earth, offering insights into potential tipping points and how to avoid them. Geologically, Venus is an enigma. Its surface appears to have been reshaped by massive volcanic events roughly 500 million years ago, wiping away most evidence of its earlier history. Unlike Earth, Venus shows no signs of active plate tectonics, a process that plays a key role in regulating our planet's climate and geology. Yet, Venus is not geologically dead. Evidence suggests ongoing volcanic activity, which could provide valuable clues about the planet's interior and the dynamics of rocky planets in general. The renewed interest in Venus has sparked a series of upcoming missions aimed at uncovering its secrets. NASA's Veritas mission, set to launch in the coming years, will map Venus's surface in unprecedented detail using advanced radar technology. By studying its topography and composition, Veritas aims to determine whether Venus's crust shows signs of tectonic activity and how volcanic processes have shaped its landscape. Meanwhile, NASA's Da Vinci Plus mission will focus on the planet's atmosphere, descending through its thick clouds to analyze their composition. This mission seeks to understand how Venus's atmosphere evolved and whether the planet once harbored liquid water. The European Space Agency's and Envision mission will complement these efforts by studying the interactions between Venus's surface and atmosphere, providing a comprehensive view of its geological and climatic history. These missions are not just about Venus, they are about placing our understanding of Earth and other planets into a broader context. Venus offers a window into the processes that govern planetary evolution, from the loss of water and the breakdown of the carbon cycle to the effects of volcanic activity on a global scale. These insights are crucial for interpreting the data from distant exoplanets and identifying those that might be truly habitable. Venus is also a testing ground for the limits of human ingenuity. The extreme conditions on its surface challenge engineers to develop new materials, electronics, and technologies capable of withstanding its heat and pressure. Innovations designed for Venus could have applications far beyond space exploration, advancing fields such as materials science, robotics, and renewable energy. Despite its importance, Venus remains underexplored. The last dedicated mission to Venus was more than 30 years ago when NASA's Magellan orbiter mapped the planet's surface using radar. Since then, our understanding of planetary science has advanced dramatically, yet Venus has remained on the sidelines. This neglect is now being rectified as scientists recognize the critical role Venus plays in answering some of the most fundamental questions about our solar system and beyond. Venus also holds cultural and philosophical significance. For millennia, it has been a symbol of beauty, power, and mystery, inspiring myths and stories across civilizations. Today, it continues to captivate us, not as a goddess or star, but as a complex world with a story to tell. Its lessons remind us of the fragility of planetary systems and the intricate interplay of forces that sustain life. As humanity looks outward, Venus serves as a guide, a reminder that understanding other worlds begins with understanding our own. Its extreme environment, while forbidding, is also a source of knowledge that could protect Earth and guide the search for habitable planets elsewhere. Venus is not just a relic of the past. It is a key to the future, offering lessons about survival, resilience, and the interconnectedness of the cosmos. Venus and Earth were born of the same cosmic ingredients, forged side by side in the swirling disk of gas and dust that surrounded the young sun. For a time they were twin planets, nearly identical in size and composition, following parallel paths of evolution. Both may have harbored oceans, thick atmospheres, and climates that could support life. Yet their fates could not have been more different. Today, Earth is a sanctuary for life, draped in green forests, blue oceans, and white clouds that swirl in its thin, protective atmosphere. Venus, on the other hand, is a vision of planetary ruin, a searing wasteland where temperatures reach 475 degrees Celsius, its landscape buried under volcanic flows and concealed by clouds of sulfuric acid. The two planets, so similar in their beginnings, have become opposites in every way. This duality raises profound questions about the nature of planets and the forces that shape their destinies. How did Earth remain stable and habitable for billions of years, while Venus succumbed to a runaway greenhouse effect that transformed it into an inferno? Are the conditions that make a planet like Earth rare, or are they part of a natural cycle that every planet must navigate? The story of Venus is one of transformation and loss. It shows how a planet that may have once been teeming with potential for life can spiral into uninhabitability through the interplay of geology, atmosphere, and solar energy. Venus's fate serves as both a cautionary tale and a source of inspiration, urging us to better understand the delicate balance that sustains life on Earth. For scientists, Venus is more than just a cautionary tale. It is a scientific treasure trove. Its hostile environment and unique geology provide insights into processes that are difficult to study elsewhere. By examining Venus's volcanic activity, atmospheric dynamics, and history of water loss, researchers can refine their understanding of planetary systems not just in our solar system, but across the galaxy. Venus's lessons are also deeply relevant to Earth. The runaway greenhouse effect that overtook Venus is a stark reminder of how planetary climates can shift dramatically if key systems fail. Earth, with its oceans, plate tectonics, and magnetic field, has maintained its balance for billions of years. But these systems are not immune to disruption. Studying Venus helps us understand how to protect Earth from similar tipping points, ensuring that it remains habitable for generations to come. Looking beyond our solar system, Venus offers a lens through which to study exoplanets. As we search for Earth-like worlds around distant stars, Venus reminds us that appearances can be deceiving. A planet of similar size and location to Earth might be a habitable paradise, or it might be a Venus shrouded in clouds and unlivable. Understanding the factors that shaped Venus's fate is essential for interpreting the data we collect from exoplanets and identifying those that truly have the potential to support life. Yet Venus's story is not just about loss. It is also about resilience. Despite its hostile conditions, Venus remains a dynamic planet, with evidence of active volcanism, swirling atmospheric patterns, and possibly even unexplored niches where life could exist. This resilience reminds us that even the harshest environments hold mysteries waiting to be uncovered. For humanity, Venus is a mirror. It reflects our own planet's fragility and resilience, showing us how small changes can cascade into planetary-scale consequences. It challenges us to better understand the forces that govern our world and to use that knowledge to preserve it. At the same time, it inspires us to push the boundaries of exploration, to confront the unknown, and to seek answers to the fundamental questions of existence. Two planets born together have taken radically different paths. Venus's journey serves as a reminder of the thin line between survival and collapse, between paradise and hell. As we continue to explore Venus, we do so not just to understand its mysteries, but to better understand ourselves, our place in the solar system, and our role in shaping the future. In the end, Venus is more than a cautionary tale or a scientific curiosity. It is a testament to the complexity of planets, the resilience of worlds, and the interconnectedness of the cosmos. Its story is our story, a reminder of what has been, what might have been, and what still could be.